maybe 15, 20 minutes. All right, here we go. We're talking about, well, why don't we do a quick recap of implicit with a trig, right? Let's do a quick recap of implicit with a trig function. Yes, we did this last time, right? Tangent of x plus y. Is that right? Yeah. Thank you, Manish. So let's do one like secant. So let's say secant of x plus y is equal to 1 over x. And I want to find y prime in terms of x. There's one of these on every single one of my Chapter 3 tests. So make sure you do them all, right? Some will appear on the tests. Some will appear on the midterms, right? Make sure you do them all. I might have a Chapter 3 review. Let me look at that today and then post it today, okay? Let me give myself a note because I'll forget. I'm forgetful. Chapter 3 review. Okay. So, when I see a trig, I see a triangle, right? That's my theme. In fact, I'm going to add to it today. When I see an inverse trig, I see a trig, and then I see a triangle. So, kind of a three-step thing. On this one, I see a secant, but I don't think in terms of secant. I think in terms of sines and cosines. So, for my triangle here, I want to rewrite this, right? So I really see what? Cosine of theta is x, right? I did a reciprocal of both sides, right? Secant is 1 over cos. So when I do my reciprocals, I get cos, right? And from there, I can draw my triangle, my right triangle, with an angle of theta. And cosine is adjacent over hypotenuse, so x is my base. 1 is the hypotenuse. And by Pythagorean theorem, I get the other side is square root of 1 minus x squared. Is everybody okay there?
X plus y turned it into theta?
Theta, yeah, it's just the angle. Remember, a trig of an angle is a ratio.
Okay.
So I just didn't want to write x plus y again. I wanted to write something simpler. Yeah, I think last class I was using alpha.
Yeah.
So I need the triangle usually about 90% of the time. Okay, usually need the triangle most of the time. So this is kind of just a little side note, right? From seeing a trig. When I see a trig, I see a triangle. When I see an inverse trig, I see a trig, then I see a triangle. Okay, so let's go for our derivative. So we're doing d dx of the secant of x plus y should equal the derivative d dx of 1 over x. Right? It's an operator. It's not like a multiply. It is kind of a multiply, but it's an operator, like square root. So what do we get on the left side? What's the derivative of secant?
Secant x tan x?
Yes, nice. So secant of x plus y times the tan of x plus y times the derivative of the inside. And I'm going to put a placeholder on that because I'm not quite ready to do it. But I want to always be thinking of the chain rule from forever and ever. Is everybody okay there with the left-hand side? Gerber, you awake? Mom, you okay?
Yeah, I'm here.
Okay. Gerber, nice. So left-hand side, everyone's okay? Left-hand side, nice. Thank you, Noah. Gerber, thank you. On the right-hand side, I should know this by a shortcut power rule, or hopefully I have it memorized already, right? Minus 1 over x squared. Everyone okay with that? Anybody want to see that shortcut power rule? Nice. I still have to take my derivative of x plus y, which is 1 plus y prime, right? Hopefully everyone is okay with that. I could have done it in one step, but I'm trying to take my time here today. So I get a 1 plus y prime equals negative 1 over x squared. Okay? I'm solving for y prime, so I want to divide by secant and tangent, right? So I'm going to divide by my secant and tangent. Same thing on the other side. Right? It's x plus y is the argument, right? It's the angle. I could put a theta in there, that would be fine. So I get 1 plus y prime equals, well, if I do a reciprocal of secant, I get cosine, and a reciprocal of tangent, I get cotan. So I get minus cosine of x plus y times cotan of x plus y all over x squared. Hopefully everybody's okay there. And now I'm going to add, subtract 1 from both sides, right? Nice. So I just want to now make sure everyone's with me here. I want to go back and replace. Remember, I want to solve in terms of x, so I don't want a cosine or a cotangent in there, right? So I want to go back and get my cosine piece out of here. Cosine is what? X, right? And we knew that from here as well, right? We didn't even need the triangle. We knew cosine was x. And what's cotan? Cotan is adjacent over opposite, right? So my cotan is coming from that ratio. So I get negative 1 minus x times x over square root of 1 minus x squared all over x squared. And it looks like the x squared's going to cancel. I hope you agree with me there. Everyone okay, first of all, before I move on, that where I got the cosine from, where I got the cotangent from? Yep, Manish is there. Noah's there. Tally. Nice.
It's tan over secant, or secant over secant, and tangent over tangent. Got that? Or yes or no?
So when I got the cosine, I got adjacent over hypotenuse, right? Adjacent over hypotenuse. And cotangent is adjacent over opposite. So that's my cosine right there. Right? And that's my cotangent right there. From the triangle. Yes, no, Jess?
Okay.
Nice. So I see an x squared upstairs, right? So it looks like I got my answer. Y prime is negative 1 minus 1 over the square root of 1 minus x squared. I could create a single fraction there. In this case, it's not that important that I do it. But if I did, right, I'd get negative square root of 1 minus x squared minus 1 all over square root of 1 minus x squared. And of course, it's kind of debatable about which one is better. In general, I want you to have a single fraction at the end. So I'd rather the right one, or I'd prefer the right one, but I wouldn't take points off in this case because let's count the strokes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 strokes. I want the minimum amount of memory. And the other one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So obviously the first one's better in terms of memory, in terms of saying what you want with the minimum number of amount of work, amount of writing. But again, because of where we're moving in chapter 4, I want things simplified into a single fraction. But either one is fine in this case. How are we doing?
Okay. Can you zoom back to the top again for a sec?
Let me get rid of some of those.
Okay, that's perfect.
Nice. I'm just backspacing on some of those. It's not letting me do it, but it's fine. Okay, we're ready to move on, but we need this theme. We need this theme. If I see a trig, I see a triangle, and we're gonna need it all through Calc 2. Okay, I don't think we need it in DiffEqs. So for the engineers or the physics majors, I'm not sure we need it in DiffEqs, but definitely through Calc 2. So we're talking about today.
Professor, I have a question actually.
Yes, no.
Is it okay to transform basically the complex identities before we move them to the other side?
Yes, yes. So it's really about your preference to, do I want to move fractions, right? Or do I want to move a single function? So it's your preference, though. I don't care either way. Markins.
Yeah, good morning, Professor.
Good morning.
Yeah, Professor, for the last one, you can just like the square root 1 minus x squared, you invested for the answer?
You're talking about the black box or the red box?
No, the one next to it. Before I get the answer, like I see like the square root 1 negative x squared was at like the numerator, but I see for the answer put it at the bottom.
Yeah, so I'm just confused with where we're looking at. So let me give you lines, okay? And then tell me where you're at. 9, okay.
9,
Yeah, so 9, from 8 to 9, right, I use my triangle to replace.
9 to 10.
Okay, from 9 to 10, I have an x squared upstairs, right? So that cancels with this x squared. But that square root of 1 minus x squared is still a fraction, right? It's still a denominator. So that's why it's still a denominator.
Yeah, it didn't become the old bottom. We got rid of the bottom entirely.
Yeah, so remember that
X
x canceled with a 1, right? So there's that 1. And I did that algebra quick. So, I did that algebra kind of quick, so you could take your time on that. Like if I was just working on that on the side, I have x times x over square root of 1 minus x squared over x squared, right? That's going to become x squared over square root of 1 minus x squared over x squared. Then I'm going to do keep, change, flip. So keep the top, right? Change the divide to a multiply, and then flip the bottom. So I skipped all these steps. And then cancel, and then I see I got a 1 over square root of 1 minus x squared. But I skipped all of that in my head.
Thank you.
Yeah, no problem. All right, here we go. This is it for the last bit that we're testing on in chapter 3. So this is 3.6. This is derivatives. If I could spell, it would be nice. Derivatives of inverse trigs. It's going to be important that if you're having some issues with trig, that you go back and review inverse trigs. Okay? The book does start kind of early with inverse trigs. So you could do section 3.6, you could start in problem 1 in the book and do them. And to figure out if you know how to do them or not, right? So do the odds, right? Because the odds are in the book. If you use MindTap, the odds are right on the screen, right? If you read the book right from WebAssign, there's a drop-down answer for the answer, right? And then if you're using the physical textbook, the odds are there, right? So figure out if you know your inverse trigs or not. I stick to inverse tangent and inverse sine, and inverse cosine is not much different, so I use those 3, right? So I'll be looking at y equals the arctan of x, which is equivalent to y equals the inverse tan of x. I just don't like that notation as much. I don't like that inverse trig notation with that -1. So I tend to use the word arctan instead of inverse tan. I'll be doing y equals the arcsine of x, which is equivalent to y equals the inverse sine of x. And of course, if you're using your calculator, you see right above the tangent key is the inverse tangent key, right? Right above the sine key is the inverse sine. Right above the cosine is the inverse cosine. And y equals arc cosine of x, which is equivalent to y equals inverse cosine of x. So it's just the way I'm saying it is different, and the way I write it is different, but they mean the same thing, okay?
The old dinosaur calculators couldn't afford to print arc sine, arc
Yeah,
cosine.
it's too long, right? Yeah, it's way past the width of the button. So these are the inverse trigs we're going to be dealing with, and we want to find the derivative of each of them, right? We want to find the derivative of each of them. I guess something that's weird that I'll do today is I'll be using a chain rule version of the function instead of just the pure function. Like, for example, in the past, we would have said if y equals sine of x, right, y prime is cos of x, right? So, but today we're going to be looking at something like y equals sine of u. Okay, so now my inside function, now that we know implicit, my inside function is an unknown function. So when I do my derivative, I have to say y prime is cos of u times u prime, right? I have to put this chain rule piece back in because we're going to be putting in some complicated functions into these inverse trigs, okay? Is this clear? That instead of just an x inside the function, I'm now going to be allowed to do any function inside, and because of the chain rule.
Yeah,
Yeah.
and you just had to do that with the last question.
Yep. So let's get on to the arctan problem, right? Ready? So this, of course, is going to be added to our formula sheet, right? We want to find y prime if y equals the arctan of x. So that's our problem. Once we have it done, we're going to include it into our formula sheet, right? Into our shortcuts in the simple version and into the, the chain rule version. Then we'll do a couple problems with it, and then we'll keep going that way, right? So if y equals the arctan of x, I see that I have an inverse trig, but I don't think in inverse trigs, right? And if I said to you, what's y prime right now, you would go, I don't know. But if I turn this into a trig function, then it's easier to deal with because I already know all my trig derivatives. So I'm going to take the tangent of both sides here, right? So, tangent of y should equal the tangent of the arctan of x. right? I'm composing the functions there, but I'm composing inverse functions. So what happens to the tangent of the arctan of x? They cancel each other out, right? So what do I get here? Right? I get the tangent of y is equal to x. And now I have, not only do I have a triangle, right? Now, not only do I have a triangle, so tangent of y is x, my angle is y, and x over 1 is tangent, and the remaining side is square root of 1 plus x squared. Yes,
So
Pedro?
we cancel like the tangents, but like what happened to the arc part? Like the
Arctan is inverse tan. It's the same
Oh.
thing. It's just a different word.
Okay.
Yep. So on that previous page, right? Arctan, the
Yeah.
whole word is the same as the inverse tan.
I remember that. I just like my brain like stopped when I said
That's okay. I completely understand that. Now I have something that I can take a derivative of, right? D dx of tan of y should
Yes, you
equal.
know what you said.
Yes, Marcus.
Why did you simplify it?
Simplify what?
Like 10. Why did you simplify it? But I see like this kind of like multiplication.
Tan of y is not tan times y. Is that what you're
Yeah,
saying?
no, I'm talking about
The other side?
the other side.
Yeah, yes, no, tan of anything is not multiplied. It's a function. So I'm putting a function inside of a function. But inverse functions undo each other, so they disappear, right? And you're left with the argument. You're left with what's the interior input. Afsoon.
Yeah, is there like reasoning or math to why, like kind of like a proof to why multiplying, like the inverse of an inverse is canceling out?
Yes, the multiplication of reciprocals, right? So you can kind of think of these things as reciprocals of each other, but it's not. So inverse functions when you're multiplying is dividing, but inverse functions when you're using a trig is the inverse trig. And so that's kind of why they're using this little inverse symbol, right? To kind of have you thinking about, but you're not dividing here. That's the thing, right? These are undoing each other, like the square root of a square, right? Squaring and square rooting undo each other, right?
Oh, I think I got it.
Yeah.
Thank you.
Yes. Markins, yes?
Yeah, I got it. Thank you.
Good. On the left-hand side, the derivative of tangent is? Anybody?
Secant squared.
Nice. Secant squared of y times the derivative of the inside, which is?
Y point
Nice. And the derivative of x is 1.
1.
So now we're solving for y prime. So I get y prime equals 1 over secant squared of y. I can go right to my triangle. Me, personally, I'd rather say that's cos squared of y, right? And from my triangle, cos is 1 over square root of 1 plus x squared. And because I'm doing cos squared, I'm squaring it. So I finally get my derivative of 1 over 1 plus x squared. Make sure you're following me here. Everybody with me?
So you took secant squared y to the other side, and that's why it went to cos secant.
Well, no, I'm dividing by secant squared, so it's downstairs. But the reciprocal of secant is cosine, so that's how it becomes cos squared.
So to move it over to the other side, it was became cosecant.
No, it's secant. That's a secant.
Oh,
It's my
it just looked like
Yeah.
looked like cosecant for some
yeah,
reason.
still a secant. I divided by it.
Okay, this is weird cursive. My bad.
Yeah.
Sorry.
Yeah, I have pretty weird cursive, like in grammar school. I got kicked out of grammar school, though, but I did my cursive like this. Get it? Cursive? Curse?
Of course.
Cursive? I can get you fired for that shit. That's funny, too. Is everybody with me in this box here?
The trick part that's like intriguing to me, like the opposite of tangent is like cotangent.
Not
yes?
opposite. Not opposite. Reciprocal. Opposite means positive, negative. Reciprocal is the flip. Numerator becomes denominator. Denominator becomes numerator.
Why we use secant? Secant is like the reciprocal of
Cosine. Cosine.
So how we find the secants all this time? It's like,
How do you find cosine? If you find cosine, you get the reciprocal, and there's your secant. So, for example, cosine of pi over 3 is 1/2, tells me that secant of pi over 3 is 2.
yes.
Soon, question.
So if derivative is d over dx, is the from earlier the tangent, or that dx over d?
No. So ddx is always an operator. Okay. The reciprocal operator is called the integral. So
Right.
we will talk about those. We'll talk about the reciprocal. I'm sorry, the inverse of derivatives. So whatever I'm taking a derivative of, ddx is my operator, or that prime symbol, right? So I could either say ddx of tangent of y, or tangent of y all prime. So that operator never flips. And I love questions like that.
Implicit differentiation is kind of like a L'Hopital, but with extra steps a little bit.
Yeah, but I mean, L'Hopital's is very specific to a fraction, right, and a limit. So we're just,
Yeah, that's true.
Yeah. Okay, so what do we have here? Let's summarize. Everyone okay with this box? Everyone okay with this black and red box I have here? Everybody followed what I did there. Got a couple thumbs up.
When you have 1 over 1 plus x squared at the end, that's because we went back to the triangle and we had the adjacent over the hypotenuse, right?
Yeah, so remember, I'm trying to solve in terms of y prime, right? So if I'm starting with y equals something of x, y prime better be something of x, right? If I'm starting explicitly, I better end explicitly.
Okay.
Good, so here's our summary so far of our new shortcuts, right? If y equals the arctan of x, y prime is 1 over 1 plus x squared. Beautiful. But I want a more sophisticated version where I'm plugging any function I want inside. So y equals the arctan of u gives me y prime is the derivative of arctan evaluated at u times the derivative of u. So 1 over 1 plus u squared times u prime. And of course, I could just put the u prime upstairs. So that's my addition to my formula sheet, my addition to my derivative list of derivatives, right? In fact, I'd really like to think of everything now as this this version. So like if I looked at my y equals ln of x, right? Y prime is 1 over x, but now I should have y equals ln of u gives me y prime is u prime over u, right? I have to think of these chain rule versions of everything now. And we'll talk more about this one on Friday. Okay, let's do a problem with the arctan of x, right? Let's do a problem. Let's find a derivative. Let's find maybe a tangent line, okay? So, keeping with arctan of x, I'm going to do y equals arctan of x squared. So first of all, do you know what arctan of x squared looks like? I don't know. I don't know if you do. We should definitely know what arctan looks like, right? Arctan looks like this. So what's my domain of arctan?
Negative infinity to infinity.
Nice. So the domain of y is minus infinity to infinity. You can see it from the graph. What's the range?
Negative infinity to infinity.
Nope.
Oh, 0.
Nope. How low
Plus
does it?
1, or plus pi minus pi
Minus pi over 2.
over 1/2.
Minus pi over 2 to pi over 2. And where am I getting that quickly from? From the tangent function, right? We know that the tangent function looks like this between minus pi over 2 and pi over 2, right? And so the inverse of tangent is arctan, right? We're rotating it, right? We're flipping it and spinning it, or rotating it. It's symmetrical about the line y equals x. Right, so if I saw the line y equals x on here, right, I gotta flip it. Oh, sorry, it's better to see it this way. Right, there's the line y equals x. So you could see I'm gonna rotate it 90 degrees and then flip it. Right, that's my process of getting from one graph to the inverse graph. It reflects about the line y equals x. So this is a graph we should know. This one is y equals tan of x, right? That's weird writing. It's a wrong pen. Of course, you can graph these on your calculator. What's arctan of x squared going to look like? So there's my y equal arctan of x squared. What's it doing to the negatives? Look at the arctan up here.
It just made it like what is it? Brackets.
Yeah, absolute value, right. It just
Yeah,
turned everything.
exactly.
Yep. Upsoon, you want to say?
What? Just out of curiosity, what would like arctan x squared, but like absolute value of that look like in the graph?
Yeah. So if I took the absolute value of arctan, it would just be a little bit lower.
Okay.
Yeah. So if I did y equals absolute value of arctan of x, right? Because the x squared, right? If you think about what's happening with the x squared, it is killing the negative, right? But a 2 becomes a 4. A negative 2 becomes a 4. So it's pushing everything higher, right, than just an absolute value. But it does something similar as an absolute value for sure. Let's find
We
the.
had like,
Go ahead.
the
Go ahead.
arctan x squared would it just look the same as
Yeah. So the black is arctan x squared, and the
yeah, we got absolute value of that would just look the same.
Oh yeah, exactly, because it's already positive. Exactly. If I put the absolute value now in arctan of x squared, it wouldn't change a bit. Right. Yeah. Nice. Let's find a tangent line. Let's find y prime. And the tangent line at x equals 1. Right? Everybody with me? So on the black curve, where there's a 1, where x is 1, I want to find that tangent line, right? Nice. So to find a tangent line, I need a point and a slope, right? So let's take care of the point first. If x is 1, y is arctan of 1 squared, which is the arctan of 1, which is what? Pi over what?
Forget.
Say it again?
2.
Pi over 2? Nope.
Pi over 4.
Pi over 4. So if you're having trouble with your trigs, you're going to have a lot of trouble with your inverse trigs. Let's get on it, right? Good, let's find our slope. So what do we know for y prime? Well, so when I have a function inside that's complicated, I like to answer a couple of things, right? Remember y equals arctan of u gives me y prime is u prime over 1 plus u squared. So you see I need some information. So first of all, what is u? It's a baby sheep. No, it's x squared, right? What is u prime? Very good, 2x. And what is u squared? X to the 4th. Very good. The class is awake and right on the money today.
So why did we add the u squared part?
Because I'm going to need it here.
Oh, right.
Yep. So y prime is, I'm ready already. I already know my derivative. It's 2x over 1 plus x to the 4th. There's my derivative. So I've got a point. I have a derivative. I still need a slope. The slope comes from the derivative, right? Don't let me go too fast. Everybody with me here? A couple of nods. 5 cameras off. How many people are here today? 4, 8. Thank you, Chris. 4, 8, 12, 16, 20. Everybody's here today. Awesome. That's an easy day for attendance. All right, I need my slope, so that's going to be y prime at 1. So 2 times 1 over 1 plus 1 to the 4th. So 2 over 2, 1. Nice. Easy. So our tangent line, y minus pi over 4 equals 1 times x minus 1. Oh, thank you, Robert, for the easy, right? For the easy tangent line. So it looks like I get y equals x plus pi minus 4 all over 4. There's my tangent line. I just did a quick LCD in my head. How are we doing?
You put the minus 1 into the other side of the function by multiplying it by 4.
Yes.
Okay.
4 over 4. LCD, right?
Right, yeah.
Yep.
Because the form is a plus b, and to get it to the other side, to get it to the other part, you made it bigger on the other side. But
I changed the
divide by the
sign.
same thing.
I changed the sign, right? It went from minus pi over 4 to pi over 4, right?
Yeah.
And then I did an LCD on the 1. I did a 4 over 4 here. All right, let's do another. Been done today, but I will get it done Friday. Right, your next homework is 9 problems. So there are 3 of them from this section. So they're difficult. So let's get to work on it right now. Don't wait till Sunday. Okay. Let's find y prime. Let's find y prime in terms of x. Okay? So I can see right away I have an inverse trig. If I have an inverse trig, I have a trig. And if I have a trig, I have a triangle. Right? So I like to say that theta is arctan of x. But I don't think in terms of arctans. I think in terms of tan, right? So tangent of theta has got to be x, which means I have a triangle, right? An angle of theta, a ratio of x over 1 for tangent, and the remaining side of square root of 1 plus x squared. How are we doing? So,
Following so far.
nice.
Yep.
So I'm really just working on the problem y equals sine of theta, right? And so what do I get for my derivative? I get cos of theta times theta prime. But theta is the arctan of x, right? So I'm really doing y prime is cos of theta times the arctan of x prime. Well, that I have memorized, and I get the cosine from the triangle. So what is my cosine piece from the triangle?
One over square root 1 plus x squared.
Nice. And then what is my arctan derivative? 1 over 1 plus x squared. And then I see I have the same denominator, but 1 is to a half power, 1 is to a whole power. So I get final answer, right? Y prime is 1 over 1 plus x squared to the 3 halves.
So we're allowed to use the shortcut on the test, like, memory.
Yes. Yes. We've been, right, I mean, this one is not easy to do. F prime of x equals the arctan of x plus h minus the arctan of x all over h. This limit is not easy. And
You're
so,
almost expected to.
well, so that's where this implicit came from. So when things are nearly impossible to do, people are just trying to discover another way to find an answer. And so the implicit makes this derivative very easy, right? I got to take a quick break, 5 minutes, okay? Come on, Luke, let's go.
not understanding the trick that we need to use most of the times.
Yeah, it's a lot of stuff you gotta review.
Like, because I took trig like around 1 year ago. Yeah, 1 year ago.
I took pre-calc 3 years ago.
Yeah, pre-calc, like I took pre-calc on high school, and like after pre-calc, like I retook pre-calc on the college.
Actually, I lied. It was 5 years ago. I took calc in senior year, or yeah, calc in senior year. It was 4 years ago for me.
Like I stopped like high school, I stopped on pre-calc, but I took again pre-calc on the college because I didn't did like the leveling test, like the test that you need to do like to know what is your math level. I decided to start from the beginning again because like I did the
Yeah, that definitely helps.
yeah, because I did the final semester online. Because of that, like I decided to do everything again.
Yeah, I'm just stubborn, and my math teacher taught me these things so many times that I expect myself to remember some of it.
Yes.
But all the trig stuff is important to know a fundamental level.
Yeah, trig, like I don't remember almost anything.
Oh, that's not good.
Yeah, like I need to review trig because like like getting all the previous one that he did, getting like the secant from like the tangent. I have no idea how he did that.
It's just well, like, you know, sine is y over x, and cosine is what oh my god, now I'm forgetting. But it's literally just one of the sides over one of the sides.
Yes.
That's literally all it is.
Okay.
It's like you can look it up, and then you'll know, because yeah, it's the same thing as sine and cosine and tangent.
I know that tangent's like opposite. No, is adjacent of the hypotenuse. No, I need to review.
Why didn't you take trig?
I take trig with you.
Well, why? I taught you what these ratios are.
Yeah, but I don't remember anymore. Like, because I took it 1 year ago.
Hey, some of us took this 5 years ago.
Well, you all better review.
Yeah, I really took trig with you. Like, I took the trig, like, if I remember, was...
You took trig first and then pre-cal?
No, I took only the trig with you. Pre-calc I took without the professor.
Right, but at the same time or later?
Yes, at the same time.
All right. Well, you got to know it, especially for Calc 2.
Yes.
Okay. Let's do another trig, inverse trig derivative. Let's do sine. So arcsine. Why is my monitor leaving? Okay, here we go. So we want to find the derivative if y equals the arcsine of x. Find, oh, I was recording all of that, sorry. Find y prime, right? So again, I don't solve things. I don't think in inverse trigs, I think in trigs. So I want to say, using the inverse here, which is the sine function, I want to say sine of y should be x. Do we agree? Once I see an inverse trig, I see a trig. Once I see a trig, I see a triangle. So I see a right triangle, and sine is opposite over hypotenuse. So I must have an x for the opposite side, a 1 for the hypotenuse, and the remaining side is square root of 1 minus x squared. Does anyone need to see the Pythagorean theorem there for that remaining side? It's fine if you do.
If we have time, we might as well show it
Got it.
really quick.
So just a quick side thought. If I have this right triangle, right, and sides of the height is x and the hypotenuse is 1, I'll call the other side a, and I know that a squared plus x squared equals 1 squared, or a squared plus x squared equals 1. So a squared must be 1 minus x squared, and there it is. A is the square root of 1 minus x squared. Okay, so we're ready to take a derivative implicitly. We're going to do d dx of the sine of
Sir, I
y.
have a question. Sorry.
Say it again.
I have a question.
Yes, yes. No.
After the triangle, what are the steps actually after we find the triangle?
So the first thing I'm doing, once I see a sine function, right, I know which sides I need. I need the opposite side and the hypotenuse. So the ratio I have is x. Well, that's got to be an x over 1, right, because x over 1 is x. So I label those sides, and then I find the remaining side with the Pythagorean theorem, right? A squared plus b squared is c squared when a and b are the legs of a right triangle and c is the hypotenuse, right? That was discovered to be known by the ancient Egyptians, not proven by them. There is a proof in 4000 BC in China. There's one in India around the same time. Pythagoras supposedly studied with the ancient Egyptians, and his name was attached to it because he published a proof, right? So anyway, we knew other cultures knew about it long before Pythagoras. All right, derivative of sine is cosine, and we're going to keep the cat in the box, but we're going to multiply it by the derivative of what's in the box, right? Y prime. And on the right side, we get a 1, right? Derivative of x is 1. How are we doing? So we get 1 y
Count
prime.
the part's easy.
Yep, y prime equals 1 over cos of y. Of course, we could just look at that. That's the same as secant, right? So we see that y prime is 1 over square roots of 1 minus x squared. Everybody see that from the triangle. So we want to take a look at our two versions that we're going to put on our formula sheet, right? And that is if y equals the arcsine of x, y prime is 1 over square roots of 1 minus x squared. And if y equals, y equals arcsine of u, y prime is u prime over square root of 1 minus u squared. Let's do one more problem today and then get the hell out of here, right?
Yeah, before we move on, Professor, can you go back to the previous page, please? I want to ask you a question.
Which question?
To the previous page.
Oh, sure.
Yes, like for the answer, how did you get like 3 over 2? Like
Yeah, so I've got 1 plus x squared. Square root of 1 plus x squared times 1 plus x squared, right? So that is 1 plus x squared to the half power times 1 plus x squared to the first power. So I get 1 plus x. So when I have like bases, I'm going to add the exponents. So 1 half plus 1 is 3 halves. Or 1 half plus 1 is 1 half plus 2 halves. And that, 2 halves, and that's my 3 halves.
I got it. Thank you.
Yeah, nice.
Oh wait, mine is cut off. Hold on.
What's cut off?
It got cut off because your face was in the way. Can you go back?
My face.
Somebody's face was in the way.
Oh, I get it. The little movable.
I had it in.
Yeah.
I had it in full screen.
Yeah, like the best
Okay,
way to watch this lesson is don't put in full screen. Was always on full screen, like it will cut like a little bit of the right side.
Pedro, where did you sit in the trig class?
No, was already on like this, like Zoom.
Oh, it was a Zoom class, and you didn't have your damn camera on.
Sometimes, like you probably maybe remember me, like one of the classes. Like, I stayed in the class because I lived in the class because I was, like, maybe on the rest, I don't remember. And, like, I stayed until, like, the calculus class.
Yes, I do. How could I forget you? How could I forget you? All right, let's do another problem. Last problem today, and then we'll go have breakfast. Okay? Who's buying?
Yeah, excuse me, Officer. Before you go, can you go, like, to the one that you did after your previous page that had it?
This one?
Yes. Yeah.
Yep, no problem. Okay, ready?
Yes.
Nice. Let's take a look at, let's say, the tangent, right? So y equals the tangent of the arc sine of x over 2. So Pedro, that one you sent me, try it again now that we've seen all of this, okay? And if it's different than this one or one I've done today, then I'll do it next class, okay?
Like, if I remember that one, we will need, like, one of the parts, it will need us, like, to do the double chain rule.
This is it. Yep. So this is an arc sine of x over 2. That's my angle, but I don't think in terms of arc sine. I don't think in terms of inverse trigs. I think in terms of trigs. So what do I want to say here? What do I want to write on my paper?
Sine theta equals x over 2.
Beautiful. Sine of theta is x over 2. As soon as I say that, I know I have a right triangle with an opposite side of x and a hypotenuse of 2. And the base is square root of 4 minus x squared. Everyone agree? You got to be good at drawing these triangles. In Calc 2, it's a huge part of one section where I'm trying to undo derivatives, and I can't. So what I end up doing is turning things into trigs. So I'm starting with x's, and then I realize what triangle I have, and then I turn it back into trigs, and then I can undo the derivative that way. Okay, the process is very difficult. usually is a game changer for a couple of students. So you've got to know this trig. So I'm ready for my derivative, right? Y prime is secant squared of theta. I'm just letting my inverse trig be theta, because I can already get this part now from my triangle, right? But now I need the derivative of the arcsine of x over 2, right? So I'm putting that there with a placeholder of arcsine of x over 2 all prime, right? So I can get the secant squared theta part from my triangle. The rest I have to do the derivative. Now I'm reminding you that I have y equals arcsine of u, right? That means y prime is u prime over the square root of 1 minus u squared. So I want to be thinking at this point, what is u, right? What's my function inside? It's x over 2. What's u prime? Who's got u prime for me? It's easy.
It should be 1.
1/2.
Oh, my bad.
Right, 1/2. X over 2 is 1/2 times x, so the slope is 1/2. And what's u squared?
Okay, it preserves the bottom of it.
That's
okay.
right, yep. What's u squared is x squared over 4. Right, I need all of that. I need a u prime, I need a u squared. Right? All right, let's see what I have. I have secant squared of theta times 1/2 over the square root of 1 minus x squared over 4. So you can see I'm going to do a lot of little arithmetic things here. I've got fractions within fractions. I have to simplify things. Let's get our secant squared from the triangle. What is my secant? Secant is hypotenuse over adjacent. So 2 over square root of 4 minus x squared squared. Everybody with me? So I got to get a common denominator in there. So I'm gonna do times 4 over 4 in here, right? So it looks like I have 4 over 4 minus x squared, right? When I square the square root, it goes away. Times a 1/2 times the square root of 4 over 4 minus x squared over 4. And I could take that 4 out, but what does it come out as?
A square of 4, or square root of 4.
Square root of 4, exactly. So I get y prime is 4 over 4 minus x squared times 1/2 over the square root of 4 minus x squared over 1/2. So these 1/2s will cancel. That 1/2 looked funky. Looks like 11/2. But those cancel. And it looks like I have a final answer of 4 over 4 minus x squared to the 3/2.
Professor, the
Yes.
double chain root that I calculated, let's open